Good day, folks. This is video number 3 or tutorial number 3 in a playlist that's called Motion Design 3D Experience, the dynamic aspects. And I will be doing a problem which is a block that's sliding on a surface, as you can see here, and there is friction between the two between the two surfaces. Now notice that there's a constant force that's acting there, and in principle, this block will go along a straight line down the track. The only thing is that, and that is a prismatic, actually prismatic joint. However, if you solve this thing as a prismatic joint problem, you will not be able to create that friction model between the two surfaces. So you have no choice but to actually make this thing as a one block on a plane without any particular joint and solve the problem. Okay. Now, let me assume that the dimensions of the block and the surface or the track are given as shown here, although the dimensions of the track, these dimensions may not come into the calculation, but because I'm going to be modeling this thing for you in the video, I have some dimensions here specified. There is a coefficient of friction, 0.1 Coulomb friction between the two surfaces, and gravity, of course, is going to be acting downward, 9.81. And based on very simple first year dynamics calculation, sum of all the forces equal to mass times acceleration. If you write the force, the applied force, and coefficient of friction, kinematic friction, times the weight of the block, this is going to be mass times acceleration. Left side is sum of all the applied forces. The right side is uh, mass times acceleration. And in here, we have everything except for A. You can calculate A analytically. You're going to get 11.89 meter per second squared. And it's a constant acceleration. Now, of course, if it's a constant acceleration, the velocity changes linearly, and the displacement is parabolic. So whatever I get, I should be matching, comparing it against these values. Now, the help in the 3D Experiences platform for this particular topic is given here on that option number 5. You'll see that in a minute, and it's not very informative. So here's the situation. When you create a model in motion design, if you go to the mechanism tab, there is a 3D contact here. If you click on it, this dialog box opens up, and we're gonna fill this in a minute. I just wanted to point out that this is not the only way to solve the problem. There are other ways, but let's move on. So let me go ahead and start with assembly design. First, I'm going to make the track. So let me insert my first 3D part. We'll call this thing the track. So there is the track, and here is the track. All right, let's go make it. It's just a long box. That's all. Double click on this thing. So I'm in part design. On that plane, I will sketch. Okay, so let me go ahead and rectangle. Let me dimension this thing to be 0.3 meters. Yep. And then let me make this thing 0.025. There we are. And we're going to exit and pad it by 2 meters. Okay, so this is going to be my track. Good. Now we're going to insert the block. Insert 3D part. I'm going to call this thing the block. Let's go make it on that same plane, vertical plane. I will sketch a box, basically a rectangle. Okay, size of 0.1 meter. All right, exit, and then pad it by 0.1. So we get the basically a box. Let me also change the color of that for cosmetic reasons, no other reasons. Let's say green. Okay, good, good. Now, that's pretty much it as far as the model, except that you just have to bring this thing down and put it on that surface. So what we're going to do is go to the assembly design, and we're going to fix the track. Is track, fix it using engineering connection. And then I'm going to bring this thing down and put it on that surface. So I can use a snap, for example, snap this edge to that edge. And there is really no joints here. I'm not going to create any joints here. Yeah, just leave it the way it is. Okay, good. If you want to hide these planes, you know how to do that. Control F. Let's search for all the planes. Look for it and keep it. Grab it. And then we're going to hide them. Otherwise, you have to do 6 hides basically. Or yeah. Just give it a minute. Still thinking. All right, so we're going to hide this. Very good. Now, we're going to go to motion design right there. Motion design. I've done this problem in another playlist which deals with mechanical systems experience and mechanical systems design. And you can see it there if you want, but we're using motion design. Now notice that what it says is that, look, you want me to create a mechanism for you, a new one? Yes. And as soon as you say yes, it creates the mechanism here. There are no joints except for the fixed track. Okay? And it also creates a scenario which by default is dynamic scenario. If you double click on this, if you double click on this dynamic step, notice that the default time is 5 seconds by 1.2 seconds because I think here calculation is done over a 0.5 second, okay, which 0.5 second. I'll do a 0.5 second. And then for settings, I use, nope, that's good. Everything else, everything is the same. That's good. Now, we're going to create contact. So look at the, over here, there are no joints, but there is this thing called 3D contact. Click on this. It says select the parts, basically select the parts that are going to come in contact with each other. Well, there's going to be the block, the two bodies here, these two, this track and the block, okay? And for contact properties, you click on it, click on it. I'm going to use the restitution coefficient is not going to play a role here, but the sliding friction coefficient of 0.1, I think that's what I had here, 0.1, yeah. Now this stiffness scaling, I'll just leave it the way it is. Just leave it the way it is. But I'm going to come back and change that later on. You say okay, good. And one more thing I want to do is oh yeah, the force. We have to do the force. So we go applied load. Now what I want to do is apply the load at the center of gravity of this block. Okay. So there are different ways of doing it. If you want, since I don't have a point there, I can, for example, go create it. See that? So create a, no, I don't want that. So let me cancel this. Let me go to the uh, block right here. Let me go to the block, create a point at the center of gravity of it, of this block. Okay, so a point has been created here. See that right there? And if you, in fact, if you zoom in, you can probably see it too, right there, that location. Good. So we go back to our scenario and we apply the load there. All right, so where is the load? Apply load, and force location is going to be that point, okay? And gravity is downward automatically, minus 9.81, and force in direction y, 100 Newton, okay? We say okay. Now, nothing else to do, just go ahead and run it. Simulate, there, done. See, succeeded. Let's go and do so look at the deformation displacement. So select the dynamic step in the result section, go to result, animate, and play it. Okay, nothing surprising. Now go and do a 2D plot. So what you can do is from the pull down menu, you can select the block, show me the position of it in the y direction. That's going to be a parabolic curve right there. And notice that the height of this is, after 0.5 second, is 1.56, which agrees with this. Not quite, but so far close enough. Let's go and add the velocity to the graph. So we go find the velocity to the graph, velocity in the y direction, add it to the plot, align, and notice that the value is about 6.289. That should be 5.94. Okay, not the same, but close. Okay, and finally the acceleration, which should be constant. Acceleration in the y direction, that should be constant. Now numbers are in the same ballpark, 12-ish, and that should be, what is that? 12-ish, but I can do better than that. Now, what do I mean by better than that? Notice that when we did contact here, there was this stiffness scaling. I'm going to change that thing to be 0.2, okay? And then say okay, and then run it. And look at the same thing right here, succeeded. So we go to results, graph. So let's look at our block, and let's look at the acceleration in the y direction. You see, the numbers are closer. Look at 11.87, 11.85 or something like that. Look, it is closer to these numbers. Now, as far as the displacement, 1.486 is good. Get that also. Displacement, let me get rid of this. Displacement in the y direction, parabolic, sure. And the value is 1.484. Look at the height. You see that 1.484, okay, and 1.486. This is why I had that slide, because not quite clear what exactly is that stiffness scaling field doing. Okay. Anyway, one other thing I want to show you here. If you go back there, let me close this. And let me go ahead and go to this track. See that track? Under bodies, track, double click on track. Notice that there are two icons here. One says rigid, the other one says rigid massless. Now, by the way, let me close this, go to the block and do the same thing. Notice that it says it's rigid with a mass, of course, mass of 7.77 kilogram. And look at the slides, 7.77 kilogram, because I did not specify the material property. However, when it's not specified, automatically it takes it to be properties of steel with the density of almost 7,800 kilogram per cubic meter. The moral of the story is that if I'm doing dynamic problem, I need to have mass, and I do have mass with the block. If I go to the track is stationary and it's to 100 and I don't know 16 kilogram, but I don't care because that's not moving. I can make it actually rigid massless, and then say okay. The only thing that has a mass here is this, the green block, not the track. And now I can go and run it. It'll run. See that? And you can go and check the results. And that was the block, yeah. And for example, if you get the acceleration, yeah, what I got before, exactly the answers that I got before, even though the track has no mass right now. But because it's not moving, it really doesn't matter. This one is the displacement, yeah. See that 1.484, 1.486. All right.